Hey folks, Mr. Bucko here with some examples on absolute value equations and their graphs. So let's get rolling here. We'll start with the general absolute value equation right here with the function f of x is equal to the absolute value of x. These bars here mean the absolute value. And the absolute value is a function in which whatever goes in comes out as a positive version of that number. So here's the table associated with this function. If we plug in -4, we plug in a -4 in for the absolute value, we get out +4. So the absolute value of -4 is +4, absolute value of -2 is +2, absolute value of 0 is 0, absolute value of +1 is +1, +3 is +3, so on and so forth. If you create all of these points here, you're going to get this graph. This is the graph of the absolute value function. The vertex of this function is 0, 0. It's the bottommost point here in this case. The domain of this function is from -infinity to infinity. That means that we can plug in any number that we want to into this function. From -infinity to +infinity, any number can go into the absolute value. What comes out, however, the range of the absolute value function is from 0, and 0 is included because you can get 0 out, all the way up to infinity. So these are, again, the positive numbers. You will always only get a positive number out of the absolute value function. You can never get a negative number out of the absolute value. Everything that comes out will be positive. And then the end behavior as x goes to infinity. So as this number x gets bigger and bigger and bigger, then the number that comes out also approaches infinity. And on the other side, as x approaches -infinity, so as we go further and further and further to the negatives, the value of the function goes to +infinity as well. So that's what we can see with this arrow going up this way. So that's the general absolute value function and its graph right there. So then we're going to kind of manipulate this a little bit and change some things so that some other things are going to happen to the function and the values. But this basic parent function we'll be dealing with here. So here's another absolute value function. How do I know it's an absolute value function? It has the absolute value bars there. So we have g of x equals the absolute value of x plus 3 and then -2. So again, we can plug in whatever we want in for x and we'll get certain things out. Here's the graph. And if we want to see where this graph comes from, these points come from just plugging in numbers. So if we plug in, for instance, 0 here, if x is 0, we have 0 plus 3 is 3. The absolute value of 3 is 3. And then 3 minus 2 is 1. So when we plug in 0, we get a 1. That point's on the line. We can find all these other points as well. You'll notice here that the vertex of this graph is -3, -2. So that's the vertex. And we can find that by just plotting those points. We're not really concerned about that in the moment. The domain, again, is from -infinity to infinity. We can plug anything from -infinity to +infinity. Whatever we want can go in. What will come out is from -2, including -2, to +infinity. And we can see that on the graph. The lowest number in the range, the lowest y value is -2. And then as we can see from the arrows going up, that +infinity we can get up to from that graph there. And then the end behavior, as x goes to infinity, the function goes to infinity, g of x goes to infinity, and as x goes to -infinity, the function goes to +infinity as well. So there's our end behavior for this particular function in its graph. Take a look at another one here. More complicated. Now we have a 1/2 times the absolute value of x minus 1 plus 2. So here's that graph. Again, we can find all of these points here by just plugging values in to generate this graph. We'll see that the vertex here is 1, 2. There's the vertex right there. That's 1, 2. We can see here that the domain is from -infinity to +infinity. Again, any number can go in here. We can plug any number in we want to. The range is going to be from +2 to infinity. We can see that on the graph here. The lowest y value, the lowest value we'll get out is +2. And obviously the graphs go up, so they go up to +infinity. And then the end behavior again is the same thing. So as x goes to infinity, the function h of x goes to infinity, and as x goes to -infinity, the function goes to +infinity as well. So we have these graphs so we can make a generalized rule here. So here's another function, and we'll kind of get to what it is here. So now we have h of x is negative 2 times the absolute value of x plus 3 minus 2. Here's all that information again. So vertex is negative 3, negative 2. We can see that right here. We could generate this table of values and draw this graph. The domain again is negative infinity to infinity. The range is from negative 2 to negative infinity because now the graph's going upside down, so it's going down. And we can see the end behavior as x goes to infinity, the function goes to negative infinity, and as x goes to negative infinity, the function also goes to negative infinity. So here's the general rule here, folks. We notice that the vertex of each absolute value graph is at hk. So the vertex is going to be at hk with the absolute value equation in the form f of x, or in this case h of x or g of x, equals a times the absolute value of x minus h plus k. So what's happening here, getting at, is that when we have an absolute value function, we can see the vertex of that function in the equation in this form, a times the absolute value of x minus h plus k. So here, the vertex of this function is negative 3, 2. We can see that here. Negative 3 because it's x minus the x value of the vertex. So if this was minus, this would have to be a negative 3. So x plus 3 is the same thing as x minus negative 3, and then negative 2. So there's our vertex. We can see it right there. And you'll notice the slope of the right half of the absolute value graph is a. So we talk about the right half. We're going to split that from the vertex here. If I just look at this line right here, the slope of this line is negative 2. And I can see that because if I start at this point and if I go down 2, right 1, I'm back on the line. Down 2, right 1, and I'm back on the line. That's where the slope is here. And then the slope of the left half is the opposite of a. The opposite of negative 2 is positive 2. So the slope of this half is positive 2. So I go down 2, right 1, down 2, right 1. The slope of this line is positive 2. So we have a general form of our absolute value equations here according to their graphs. So let's find the equation for an absolute value graph. Let's do this and work backwards. So here's our graph. What does the equation look like? Well, the first thing that we want to identify here is what's the vertex of this absolute value graph. The vertex is right here. The coordinates for this point are 2, negative 3. Vertex is 2, negative 3, so we have our hk. There's our general rule here. So our hk is 2, negative 3. So that means that h is going to be 2. Our k is going to be negative 3. The slope of the right half of the absolute value graph is a. So the right half right here, that's the right half here. So I have this point, what's the slope? I have another point right there. So if I go up 1, 2, right 1, 2, 3, it looks like the slope of this half is positive 2/3. Subsequently, the slope of this half should be negative 2/3, so I'll use these 2 points that I have. Up 2, left 3, that's going to be negative 2/3. So we have all the information we need. We have our a is 2/3. So the right half is 2/3. We have our vertex, hk, that's 2, negative 3. Let's plug that in. Vertex is 2, negative 3. Slope is 2/3. Therefore, our equation is going to be e of x, or f of x, or whatever you want to call it, 2/3, that's the slope, or a, times the absolute value of x minus 2, and it's a minus 2 because positive 2 here, minus 3, because that's our k value. So we can find the equation of an absolute value graph by just seeing the graph, identifying the vertex and the slope.